Let's consider a particle with a position function given by this here, where we have some time dependence for our I hat motion, or our motion in the x direction, for our j hat motion, and for our k hat motion. And the units of this are meters. So what's the velocity? Well, we have position. We can take the derivative with respect to time to get velocity. The derivative with respect to time can be broken down into considering each of these positional components in their own way. So they're all linearly independent here. They're not combined. We can split it up and just take the time derivative of that first time dependence, add on the time derivative of the second one and the third one. The units will be meters for this whole thing. In doing this, we'll use standard rules for taking derivatives. This 10t would become 10 minus 2t. So 10t becomes 10. The minus t squared, you multiply by the 2, and subtract 1, and it becomes minus 2t. This one here, 5t, would become 5, and this 5t would become 5. And so writing that out, you get the 10 minus 2t in the I hat, plus 5 in the j hat, plus 5 in the k hat, with units of meters per second. Where does the second come from? Well, the second comes from our time derivative. It divides by time. So far, so good. What about acceleration? Well, we can do the same thing. We take the derivative with respect to time and split this up into the I hat component, the j hat component, and the k hat component. One thing to note here is that when you have a constant value like 5, the derivative of that is going to be 0. So we'll have no acceleration in the j hat or the k hat. And we will have some in the I hat because there is still some time dependence there. So we end up with negative 2 in the I hat, plus 0 in the j hat, plus 0 in the k hat, with units of meters per second squared. Again, the per second squared. The extra divided by second comes from taking a time derivative. So rather than writing out all of this with the zeros on things that don't have components, we'd probably write it like this. Our acceleration as a vector is going to be negative 2 in the I hat with units of meters per second squared, which is a constant acceleration. We can look at this behavior in 3 dimensions by plotting it. Here you can kind of see as you track along some of that behavior. We've got our x, y, and z positions, and you can see the behavior as your time marches along. You can see this is on the xy plane, these sort of shadows there, and you can see the stars marking like where the actual particle is moving according to this positional function.